So welcome everybody to the final webinar of SINTEC project. My name is Sara Tana, my company is Warrantab, and together with all the other partners of SINTEC project, we would like to thank you very much for being here today. I know that someone of you has followed the project since the beginning of the project, someone otherwise will not have any information about the project. So the aim of this event is to disseminate and to communicate to you the results achieved in this project that now is coming to the end. So I will be very brief only to inform you that this event will be recorded. So if you don't want to show your face, please take your camera off. I ask you also to the speakers to switch off the camera now and to switch it on when you will have your presentation. And I think that now we can start. The first speaker that I would like to introduce you is the project coordinator of SINTEC project, Claes Hort from Uppsala University. Hi, Claes, welcome.
Hi, Sara. Thank you for that. I'll just share my presentation.
Yes, sure. Claes will present you the project, so you will have the chance to understand more about what the project is about and the general results achieved. So Claes, many thanks. The stage is yours.
Thank you so much and welcome everyone. Thank you for being with us. So we have been working together now for 4.5 years. My background is in microsystem technology and material science, especially working with manufacturing and the micromechanics of soft materials. So together we are partners of 8 groups, and the background is that something like 6 years ago the Commission was somewhat frustrated that although for more than a decade there have been investments in stretchable electronics, there were no industrialization yet. So there was a call on how to improve manufacturability and to reach industrialization of such. Now, our suggestion, and that is also what we have shown, is how to use the digital printing technologies of solid mount technologies that are used for solid mount assembly of printed circuit boards into digital printing of smart patches, which is close to additive manufacturing and sustainably very well, as we'll see later on. Our vision was that by doing that, we would provide soft, sticky and stretchable sensor patches that could be used multiple times, longer periods for anyone, anywhere and anytime. So providing something that could withstand action, sweating and water, making it ideal for an active life. And by having it stretchable, to keep it on the same position and reducing motion artifacts, by that increasing capacity of both intra-body communication and sensoric inputs that would allow large bandwidth at low power and secure communication. Our objectives were to demonstrate manufacturing, to demonstrate compliant and stretchable multi-use smart patches, to demonstrate the advantage of compliant and stretchable systems for electrophysiological sensing, and to validate these for rigid stretchable integrated technology and demonstrate these applications in clinical environment and sports performance. I can proudly say we've been able to achieve all the objectives. This is due to the SINTEC hardware offering. Here you see soft and stretchable sensor patches and thin and soft multi-use modules. And these modules are set under the patch for comfort and protection. It really helps when you are, for example, in a racing suit, and when you undress or dress. It sits much more tighter than when you put the sensor module on top of the patch, which is common today. Also, the softness, the lightness, the thin structures improve very much the user friendliness. With that, we created a networking platform for the demonstrations. So it was displayed in all main components, and the integration of all sub-components have been done with support and maintenance activities in the demonstration phase. And we have shown these applications both in medical and in sports performance. You will hear much more about that, and I'll just, with that, I want to thank you for the attention. Thank you, everyone.
Many thanks, Klas. Thank you
And
very
I'll
much for this
stop sharing.
introduction. Thank you very much for your introduction. Of course, now we go on with the presentation. And if you have any question, you can write in the chat or wait at the end of the event, where we will have a Q&A session, and you can ask whatever you want to our speakers. So now we go deeper in the results obtained, and we will focus on the electronics hardware. I have the pleasure to welcome Alessandro Gumiero from ST Microelectronics. Hi, Alessandro. Good afternoon.
Hello. Hi. Good afternoon. Sorry for the illumination. It's not very clear, but I'm here.
Don't worry. Don't worry. It's perfect. So if you want to start sharing your presentation.
Yes, I share the presentation. I don't know if you see the presentation or the notes. I think the notes.
No,
okay.
Okay, now we see it in presentation mode, so the stage is yours. Many thanks.
Okay, so I'm Alessandro Gumiero from ST Microelectronics. I'm an electronic engineer, and in SINTEC, together with the partners and also my colleagues, we try to develop the part relative to the hardware and all the things relative to this part. So if I can, okay. So in my group, in ST, we try to develop application. We try to do the job of our customer and try to develop application in medical field. And we, in our history, develop different devices related to this. Final devices just to demonstrate that it's possible to do, obviously, with ST components and so on. But we try to develop something on this field, especially maintaining, keeping the attention on what is the usability of this system, and also the comfort of the system, because it's very important in the medical practice and also in general for the wellness and healthcare. It's very important to be not perceptible or less perceptible as you can, because the bulk and the weight of the solution many times affect the solution itself and also the reliability of the data you go to acquire. And this is perfect for the SINTEC, because it's the center point of SINTEC, just to be able to not be perceived by the user, the final user. So in general, what we try to do usually in our job, and especially in SINTEC, was to embed all the possible functions, the usable function inside the unique devices to acquire all the possible vital sign and parameter and signal, but also to enable the possibility to combine different signals, vital signals, like, for example, ECG and PPG together, without use a very bulky solution or a very difficult to use solution. On top of this, we try to use, obviously, you can understand from our side, the ST components, but starting from what ST is good to do. So using integrated circuit dedicated not originally from the wearable or for, let me say, medical field, but for example, for mass market and for consumer. And this chip has the quality to be from the beginning low cost, cheaper, and also easy to use and low power. And this is very important in our field, also in medical, for the things I said at the beginning. So to be not perceptible by the user, but also do not occupy a lot of space and to use a very low amount of power. So in this slide, you can see two examples of what we actually used in the SINTEC project. One on the left, you see a sensor dedicated originally from used in the camera, photo camera, to reduce and to correct the white. And on the other side, we can see another MEMS sensor dedicated to usually to motion detection, but in this case embed also a peripheral capable to detect biopotential, potential in general, and we try to use biopotential. Obviously, we use all these things, try to guarantee a medical grade reading. In parallel to this, we develop, obviously, if you want to use something very cheap, very low power, you have also to understand very well what you're reading and be able to correct and use the right algorithm to detect and compute all the parameters. So we develop also some strategy, methodology, and algorithm together also with our partner in SINTEC for certain kind of parameters, but be able to develop something very reliable and robust under point of view of computation using artificial intelligence approach. Here we have example or also ordinary, let me say, analytical approach, a normal analytical approach, but anyway, to guarantee always the medical grade as a target. So in this case, I reported two different examples. One on the computation of the SPO2. SPO2 is a normal, very known, let me say, parameters, especially during the COVID period, was very known and very used to understand the amount of oxygen in the blood. So it's something quite old, but we address it in a new way just to reduce the amount of signal necessary at the beginning to compute it. And on the other side, we try to develop a computation of blood pressure analysis. This is a very useful parameter, but using also in this case, reducing the amount of data you need at the beginning and also the invasiveness of the solution necessary to detect this blood pressure. For both of these parameters, we need just only one photoplethysmography signal. And that's it. Starting from this, we develop for SINTEC, different together with Uppsala and also other partners, we develop some final, let me say, prototype and architecture. Here you can see a imaging representing quite all the things we developed, but not all, obviously, where are present the different parts dedicated to the hardware, to the embodiment, and the box, and this kind of things. At the beginning, so going deeply on what we did for SINTEC, we started from the general architecture, starting from the idea that the architecture for a body area network has to be modular, multimodular. So you can think to have a collector, a gateway that is able to detect and to collect all the data coming from the different part of your body. Obviously, we have to think about a different kind of sensor because you have to detect ECG, and to detect the ECG, you have to stay in certain parts of the body for sure, with the heart in the middle. Motion detection is important to differentiate maybe from legs, from arms. So you have to be able to put your devices on different parts of the body, also for this. Also for the other things, maybe for the optical part, you can put on different part of your body, but the signal coming from that that sensor is different. After this, we developed the idea. We think about the idea of the models. Obviously, we cannot think to have all the things stretchable because we start from something that is not stretchable, so the integrated circuits. So we added to, we we were in the situation to think about something capable to connect something rigid to something stretchable. And after different trials, we understood that it was not possible to connect the directly rigid part to stretchable part, but we were in the situation to find something in the middle, to put something in the middle, and we constructed and designed a complete solution with starting from something rigid, reducing at minimum the area of the rigid part, passing through something stretchable, something flexible, sorry, and at the end, the stretchable part connecting all the parts together. After this, the definition of the architecture, we passed to designing of different hardware. I have to say, this is I represented, I report here the last one we developed for SINTEC, and we can say the finest board for SINTEC, capable to embed a lot of different signals. The most important, I have to say, what I reported already in some slides ago. So ECG, the capability to read ECG, the motion, a complete motion reconstruction with 9 axes, and photoplethysmography and so on. So the capability with an MCU already embedded to do a real data fusion, applying artificial intelligence approach, what you want, and send this data through the Bluetooth, and manage the data, the sending through the Bluetooth, or other things also, but we are talking about something wireless at the moment. The characteristic, without to lose a lot of time, are these very reduced. We try to keep the dimension very shrink, and obviously the entire board is bigger than what is really necessary, I have to say, but we leave here are already present, are still present some part dedicated to the debug, but the board is able to be divided into parts. So also the power consumption, we reduce at minimum as we can the power consumption of the board, putting as a target 5 milliamps in this case. At the end of the story, all this part can be put together and connected to the stretchable parts. This guarantee let me say, flexible architecture, because not flexible, mechanically flexible, but not only mechanically flexible, but also under point of view, of a logical point of view. So you can connect different modules, different battery, just changing the part, the disposable part, so the stretchable part. And another point, very important point in this architecture, is that the stretchable part that connects all the things is the unique part that is attached on your body. So the feeling is to have a, let me say, second skin, because all the rigid part and also the flexible part are free to move inside on below your stretchable part, and the rigid part are reusable, because we put a lot of attention on reusability of the solution, reducing the disposable part just only to the stretchable patches, let me say. So snapshot of the different readings. We have ECG for, I put again the image, but it's just to represent the ECG we are able to read with our device. We try to use directly the patches developed, so to read the variation in impedance. So measuring the variation of stretchable lines, we are able to in certain way to detect, for example, the breathing rate if you put the patch on your chest, following the variation of the lines, or if you wanted the movements, if you put the patch on the other part of your body. Another reading we can do is related to the bioimpedance, so the impedance of the body, useful for to detect the amount of fat in your body and these kind of things, or also in this case the respiration again if you put the bioimpedance reading on your chest. And that's it. So thank you. If you have a question.
Many thanks, Alessandro. Very nice presentation about our electronics part. If you have any question, you can put your hand up or write in the chat. But in the meantime, we will focus on the next presentation, that is about the stretchable PCB technology. So now we have with us Gustav Martensson from Mycronic. Many thanks for being here, Gustav.
Hey, everybody. So I'll start sharing.
Yes, please.
Yes, ma'am. And we're on this screen and out of the way. There, you should see my first slide.
Yes, I confirm that the presentation is in presentation mode, so we can see it very well. So the stage is yours.
All right, perfect. So my name is Gustav, just as Sara said, and I will be talking about a natural extension of what Alessandro was talking about from going from the sensor package, which is one part of the actual device, to the actual production of what I call a sustainable digital production of wearable, soft, stretchable electronic devices. Now, I work at Mycronic, but I really want to include Jan Maaslik from Uppsala University, who has been instrumental for the actual testing of these different methods, together with the other partners and the devices from XT. So we're talking about assembly of electronics, and Mycronic is a company that manufactures automation solutions for what we call surface mount technology, production solutions for the contemporary electronics, which is essentially based on rigid printed circuit boards. So this is essentially a cloth of resin and glass fiber that is rigid and used in all contemporary electronics, or a majority of it. We load this into a system, we deposit some kind of conductive material, or mounting adhesive or conductive adhesive. You have to mount components thereafter. The components have to be stored somewhere. After they're mounted, you have an inspection step. In traditional electronics, there is a reflow process to melt the solder paste so that we have connection between the components and the PCB, and then some collection or unloading with a follow-up inspection or testing method. Now, we're going from here to look at these stretchable solutions. And within the SINTEC project, as Alessandro started talking about, we've gone through a fascinating iterative process of looking at very simplified devices with a sensor chip from ST, stretchable interconnect lines, and an energy source. Understanding this and making it more refined, or an ECG patch with our energy source, our sensor chip, and then Molex connectors to make the not only the production of this easier, but also from a sustainability aspect. So in this presentation, I'm going to be talking both about assembly and sustainability. This went further to even more refined processes with a combined energy and sensor source with a Molex connector, and then what is, at least at present, our device looks something like this. So this is this novel device. In this case, it's the ECG patch, where we have our electrodes here, our stretchable interconnect lines, a connector, which is essentially a simplified USB connector, another interconnect line to our other electrode, a stretchable surface, and then our sensor module. Connected, you'll see something like this, and to put this into scale, it's about this big. So this is our stretchable device with our connector, our electrodes. So this is what we would like to be able to produce. Now, going from this, what we want to do is use the same kind of production devices. So we don't want to reinvent the wheel, but use the same wheels, but in a new way, to produce a panelized board with our multiplicity of devices. And what we propose then, our first part of the project, is essentially looking at the producibility of this using existing production machines. So what we produce in this case is a loading process. And then before we connect our connector point, the little USB point, we have a jetting stage where we have a non-contact jetting of an adhesive. So this is our device here. After that, we place our connector pad using a suction-based pick-and-place process. We have an optical inspection. This is all in contemporary electronics production. The inspection process to ensure reliability and repeatability is key. After that, we have our interconnect lines, the stretchable interconnect lines that have a two-step process where we can either jet or contact dispense, and I'll come right back to that very soon, the liquid metal interconnect lines. And in the same machine, do a jetting of a coating process so that we have a UV curable stretchable coater for our interconnect lines and parts of the interconnector. And further inspection step after that, and then a curing station for our UV curable device. You can naturally use a heat curable process, but this affects an important process of this, because it's not just being able to do the device, to assemble a device, but we will have to assemble it in a commercially viable way, where one of the key production indicators that we have in this process is that the cycle time. So essentially, how often can we produce boards? And here we had a cycle time of relatively conservative 4 minutes per module. And in this step, the question is, how often can we get a board out of this process? So we're looking at what is the bottleneck here. For these, loading is approximately 5 seconds, jetting is 15, perhaps 20 seconds, placement is very short at 20. We don't have a lot of components that we're printing. Inspection is very quick at 20 seconds at most. Here we have a question of either jetting or dispensing, and the jet process, which is a non-contact process, is much quicker. So here we have a factor 4 difference by 2 by 15 or 120 seconds. Inspection, once again, quickly. Curing is very quick for these thin surfaces, and then unloading. Now, why is this still a question about the dispensing? And this is only for the liquid metal alloys that we're working with, which is a very novel process in itself. So this is a process that Jan has been working on, and this is established and has been used in the devices that have been used. So we have actually a capillary needle that is dispensing, in this case, approximately 100 to 200 micron lines with a pitch of 0.5 millimeters. They're very repeatable, but they have a demand on very high accuracy with respect to the distance to the surface. What we want to do, and what we are testing still, and we have shown a proof of concept, is the non-contact jetting process, where we essentially, more like an inkjet process with a much bigger nozzle, are jetting out these and traveling at much higher rates. So here is a proof of concept with individually non-contact jetted liquid metal alloy droplets, creating an interconnect line that could be used instead. This is work that is ongoing, and due to the low viscosity of this, so it flows very readily. It's just twice the thickness or material thickness of water. It demands a very small nozzle to make sure that we don't have any leakage of this material into our system. We're also doing tests on rheological manipulations, actually affecting the flowability of the material to make jet dispensing easier. This is something that has actually shown a lot of commercial interest in the recent months, and approximately 18 months. Like I said, this is not just about assembly possibility, reliability, and repeatability. We have a sustainability perspective also. And this started actually at a very opportune time for Mycronic itself, that in 2015, a few years before the SINTEC project started, there was a demand from the EU that large companies present what they are doing for their with respect to sustainability for their companies. And what we identified at Mycronic is that if we look at ours, I apologize that this is in Swedish, that if we look at Mycronic's carbon dioxide footprint of 59,000 tons per year, a majority is the use of the product. 78%, transports and travel is 14%, use of material is 6%, and our actual facilities is about 1%. So it's very important for us to actually think about how our machines are used and the use of energy that they have. So within the SINTEC project, we produced or carried out a life cycle analysis of the process of production and compared a traditional SMT line and an equivalent rigid ECG patch with our sustainable digital process for our stretchable device. And what I show in these two plots, we focus on the left one first. If we divide this into raw materials, manufacturing, and end of life, we have a comparison of the comparative impact of rigid process and a stretchable process. So for all of these, from materials, which dominates, to the manufacturing step, to the end of life, our digital stretchable device has a lower impact by an effect of less than half, say about 40%. And if we look at the actual impact with these traditional different factors such as climate change, ozone depletion, terrestrial acidification, and the other 15 different categories that we've divided this into, if we look at the impact normalized by the actual the rigid device, so this is the impact from the rigid device, and the blue is the stretchable device, we have consistently lower, approximately less than 60% of the impact. And by chance, we see that, let's see, I can't go forward here. There. Our key performance indicator that we chose for this was a stretch goal, was that our ecological impact from our stretch production process would actually be 60% of that for the rigid production. And we end up slightly below that, actually, if we look at this. But perhaps we shouldn't equate all of these impacts. So from this, essentially, we have two different aspects. We have shown that there is a commercially viable and technologically acceptable production process, and we've also looked at the ecological impact that from a single study instead point us in the direction that this is actually a ecologically advantageous method as well. And that's all from me. I'd like to thank you for your attention. My name is Gustav, and I'd be happy to take questions after the rest of the presentations. Now over to Robin, I think, if I remember correctly.
Yes, many thanks, Gustav. Many thanks for your presentation. Yes, we will have time for a question at the end of the event. We have a question already written in the chat. We have seen it, so we will answer it later on. Now we have talked about the hardware and the stretchable part. I would like to thanks to Professor Robin Augustin for being with us to give the next presentation that will be about comparative communication studies. That is another important and innovative part of SINTEC project. Hi, Robin.
Hi, Sarah. Good to see you.
Welcome. Good to see you too. Do you want to share your presentation?
Thank you, if I may. Thank you so much.
Many thanks. Perfect. We can see it correctly. So if you want to start, the floor is yours. Many thanks.
Thank you very much, Sarah. And this is a wonderful opportunity to show what has been happening in this work package of ours. So we've been responsible for the communication part of SINTEC, and it is about this new technology called fat intraverted communication. And I'm Robin Augustin from University of Uppsala. So our task had been to push the technology, which is about intraverted communication, from a TRL, which we started with in the beginning of the project, which is TRL3, to higher TRLs like TRL4 and TRL5. So let me give you a background about this communication technology, which is rather unconventional compared to the existing human body-centric communications. Probably you know about this Bluetooth communication, which is a microwave-based or radio frequency-based communication technique, which is being widely used in wearable devices. There are also other communication techniques such as galvanic coupling and capacity coupling, which are also different styles of communication where you use the human body as one of the communication channels in order to establish reliable data transfer between two nodes that are mounted on the body. So in our research, we are a little bit uniquely positioned in the sense that we are not using any of galvanic or capacitive communication in our technology, but we are using micro communication, but not in the same focus as Bluetooth would operate. Here, what we try to do is to channel microwaves within the readily available, in the sense that, okay, everyone as human beings do have subdermal fat. So the idea is to channel a couple microsignals from the outside of the body, from the exterior part of the body, from the surface of the skin, through the skin into the fat channel, which is placed in between skin and muscle. So it conveniently creates a waveguide between these conducting layers of skin and muscle. And fat is a good transmitter, or let's say the micro frequencies or the micro signal, micro energy can easily be transmitted through the fat because it acts as a dielectric. So if you read it together, the skin, fat, and muscle, you can consider as a 3-layer waveguide where the central layer is supporting the transmission of the signal. So pattern robotic communication, as we define it, is a methodology by which microsignals are excited in the subdermal fat layer, which is situated above the muscle layer, beneath the skin layer, through an implanted node, either an implanted node, a surface, or a semi-implanted node, or even a surface node. Here in SINTEC technology or in SINTEC project, we have used a completely non-invasive solution where our antennas or the interfaces are situated on the surface of skin. So we have, in the context of the SINTEC project, did some trials in order to, bring the technology across different experimentation stages. Of course, we started with lab experiments where we have created phantoms. Phantoms are representatives of human tissue in terms of the dielectric properties of it in the microfrequency spectrum. And after doing phantom experiments, we have moved on to animal trials where we have done pig trials in order to transmit signals through the fat of the pig, which is subdermal. So we have had different nodes placed on the belly part of the pig and try to communicate between different nodes. Some of the nodes were connected to sensors, some others were connected to actuators, and a logic combination of the sensorial inputs creates execution of certain actuators which are connected to their external nodes. So I briefly mentioned about phantoms. In the context of SINTEC project, we have developed phantoms which were representations of human torso. And in order for the technology to be proven, we have to prove that the technology would work for different morphologies of human body. And we are classifying two extreme morphologies of human body, which is, so-called athletic body type, where we have very low water content, athletic body type, which has very low fat content, and also obese body type, which has a higher fat content, right? For higher fat, subdermal fat thickness. So if the technology works in both morphological spectrums, both end of the morphological spectrum, then it is intuitive that it would work in any of the morphology type, which is in between the athletic and obese types. So phantoms are made in-house in the context of the project, where we have made phantoms which has a long shelf life. It can stay more than a year and a half without deteriorating its properties. And it could be not only used for fat IVC communication, but other type of body area network-based communications. So these are the antennas that has been used in the study. The antennas that you see on to the right had been developed together with ST Microelectronics and has been integrated onto sensor nodes. For example, here in the center, what you see is a photoplethysmograph. And they had been, compared with respect to standard BLE nodes or BLE antennas. So we have done the initial set of trials in the phantoms, both athletic and obese. We have seen that in comparison to BLE, low energy Bluetooth communication technology, our fat IBC technology has a superior performance. And for fat IBC, we have made different kind of interfaces. And the difference in the interfaces is basically in the efficiency of those interfaces in coupling signal into the subdermal fat layer. I mean, skin is always a very strong, a very good isolation medium from the external environment towards inside the body. So you have to penetrate through the skin barrier, and this is really a task to perform. So we have, in this respect, devised two antennas. One is a U-shaped, another one is a ring antenna, So linear polarized and circularly polarized antennas, and we have seen that the circularly polarized antennas do have a higher efficiency compared to the linear polarized antenna or Bluetooth in its performance in terms of coupling the signal into the fat shell. So as you can see that we have also done under the ethical approval that we have obtained in a national project in Sweden, human trials where we have tried it on athletic humans and also obese human subjects. And we have done extensive experiments so that we can analyze the performance of the fat shell. So there is also a component of this surface wave that exists between the skin layer and the air, the interface between air and skin, so which contributes to the surface coupling between two nodes also present in the BLE. In order to take away that ambiguity and to establish more the fat interbody communication, we also have devised a chamber that isolate the surface wave component. And that's what you see on the right side of this image. So there is a septum that divides the phantom so that any surface wave component is being cut and the channel is being transmitted by virtue of the fat IVC or the fat interbody channel. So in the results, we could also see that in terms of the performance, the circularly polarized antenna, which is the ring-shaped antenna, performs better compared to the BLE, and also the U-shaped antenna, which is linearly polarized. This is because the coupling into the fat channel is more effective due to one type of excitation compared to the other. And this finding has been consistent for both athletic and obese subjects. So we also see that the propagation channel has a similar kind of channel loss effects or channel path loss, it is called. So that's why you see similar trends in the curves, basically. Thank you very much, and if you have any question, we will be very happy to answer that.
Many thanks, Robin. Very interesting point that, of course, have been followed in SINTEC. So it was really, really nice to hear from you. If you have any question, of course, write in the chat, and we will be able to answer at the end of this event. Now, I would like to introduce you to our next speaker, that is our project partners, our Spanish project partners from MySphera company, Juan Carlos Naranjo. His presentation will be about the networking platform, sensor, and data handling. So many thanks for being here, Juan Carlos.
Hello, good afternoon. Thank you for inviting me to present this part of the project. I'm going to share my presentation.
Perfect.
Okay, here it is. I think that you can see it, right?
Yes, we can see it. It is already in presentation mode, so the floor is yours. Many thanks.
Okay, thank you, Sarah. Well, my name is Juan Carlos Naranjo. I work in MySphera as project manager, and my background is computer science. So you can imagine more or less what is the content of my presentation, that is about the network platform and the sensors and how we sensor and data and how we can and being able to handle all this data. So basically, the challenge that we have is we have very nice sensor, stretchable sensor, that are able to transmit data in I would say in a significant sample rate, 128 samples per second in some of them. So we should be able to receive all this data from different sensors and from different, let's say, capture session at the same time. To where, how we handle all these issues. So we have to understand how the data is transmitted, how we should store the data in somewhere, how to manage the sensor handling, start, stop, reconfigure, set parameters, and so on, how to exchange data with other systems, not only to the internal platform, but also with other analytics tools, for example, and yeah, how is the better way to share this information. So this was the challenge that we have at the beginning of the project. And okay, we specify some requirements for this platform based on this challenge. So basically, we should support a large number of sensor and gateways, okay, for capturing the signals. in both domains, in sport and healthcare. We should process this data and provide a convenient storage for the signal for further analysis. One thing that we have in the beginning is that we don't want to start the platform from scratch. So we started with a very well-known IoT platform that is FireWare. I will explain later how we use this FireWare platform. Of course, as I said before, should be interoperable in the sense of exchanging information with potential healthcare systems, EHR or whatever, in the case of health applications. Of course, very obvious, we have to control the capture session. We have to provide tools for the doctors or for the coach to start, stop, and make all these things related to the capture session of data. The platform should be extensible and scalable. And of course, as we are dealing with personal data, we should a secure platform. So this is the landscape that we have in the beginning. And okay, the first step was, okay, the first problem was how to receive all this data from the different sensors. Then is when it appears a device, a SINTEC gateway that was developed by another partner, Evalan, to collect all the information coming from the sensors. This communication is based between the sensor and the gateway through Bluetooth Low Energy, and from the gateway to the platform using 4G or LTE and communications. Okay, so okay, we at least wanted to support 8 sensors at once, and this SINTEC gateway should also manage, as I said before, the different configuration, start and stop commands for that. As a protocol, I will explain a little bit later also, the protocol between this gateway and the platform, we choose a very well known also protocol that is MQTT. So this is the big picture of the platform. You see in the left the sensors and the gateway that I already mentioned. And starting from the SINTEC gateway, we have all the components, but that are basically based on the FireWare platform. There are different modules related to security, related to the database, related to the dashboard, related to extension of the FireWare platform, and also the solution that we choose for exchanging information, that is the Fire standard. So starting from FireWare, FireWare is a reference open architecture and implementation for an IoT platform. It was developed in a funded EU project many years ago for handling IoT devices, and is the reference architecture for this. It's basically composed by components that are called enablers, so that are different components that manage different parts or different specific functions inside the system. For example, the big data infrastructure, the historic data, the different interfaces with devices, and so on. And in this sense, what we did in SINTEC was to develop a specific enabler for support the sensors and the IoT gateway, the SINTEC gateway. The first element to use for, let's say, manage all the different streams of data that we should be able to manage, we implement the MQTT broker. We deploy the MQTT broker. MQTT is Oasis standard messaging protocol for Internet of Things, and the characteristic is that it's very lightweight, so it don't provide too much overload over the communications. It follows a very well-known subscriber publishing pattern for the communication. That means that there is only one subscriber or several subscribers that push data to different queues, and the subscribers get data from the different queues, just subscribing to the different the interested information that they need. Well, I mentioned before also that we were very interested in the extensible and the exchange of information with other systems. So that is why FHIR appears in STEAM. FHIR is a standard for healthcare data exchange that is provided or published by LCL7, an organization that manages a lot of things related to healthcare standards. And basically now is something that you can find in almost EHR system that is in the market. So it's a standard for communication and exchange of information. It was very interesting because using FHIR not only give us this exchange of information, but also provide us to SINTEC a good data model for the data that has been received from the sensor. That was very interesting because we didn't think too much in how is the data model behind the platform. We choose these entities that were provided by FHIR, for example, the observation entities, the procedure entities, and so on, all things related to the management of sensor and healthcare data. Finally, of course, this platform should be operated by doctors, by athletes, by coach, ones, whatever. So basically, we, on top of this platform, we have created a web-based tool that that works in laptops, in tablets, in mobile phones, to configure everything related to the platform. Basically, adding sensors, configure sensors, create procedure to capture data, start and stop the different sessions of capture data, and of course the representation and the download of the capture data for further analysis. And I think that's all. Thank you for the opportunity to share this part, very interesting part of the project with you. And I think that the question will be later. Come.
Yes, many thanks, Juan Carlos, for your presentation. Yes, question will be later on, but if you want to prepare some question, you can write in the chat, and after we will read. I can see there are already 2 questions, but we will read them at the end of the event. Now we would like to share with you the results obtained in the application of the SINTEC Smart Patch in 2 different fields. The first one, it's a clinical application. So for this part of the project and these results, I leave the floor to Valeria Figini and Francesca Boschi from Links Foundation. Hi guys, and good afternoon.
Hi everyone.
Girls, hi girls.
Okay, thank you to be here. I hope you can hear me.
Yes,
Okay,
we can hear you very well, and we can see also the presentation. Many thanks.
Perfect. Okay, me and Francesca will present our work on clinical application that is mostly focused on blood pressure estimation. First of all, why we decide to focus on blood pressure? Because nowadays it's very clear how important is to monitor blood pressure to reduce the risk of several diseases and prevent them. Monitor blood pressure can help to reduce the risk of hypertension. Hypertension or high blood pressure happens when the pressure in blood vessel is too high. In particular, when the systolic blood pressure is higher than 140 and the diastolic is either of 90 millimeters of mercury. The systolic is the maximum peak and the diastolic the minimum. Hypertension is a common condition, but can degenerate if not treated, and it is estimated that 1.28 billion of adults aged between 30 and 79 years have hypertension. and only the 54% of them are aware of that condition. If not treated, hypertension is one of the biggest risk factors for CVDs, cerebral stroke, and renal failure. Nowadays, hypertension is a major cause of premature death. And there are several risk factors that include sedentary life, obesity, use of alcohol, and so on. One of the global targets for not communicable diseases is to reduce the prevalence of hypertension by 33% between 2010 and 2030. So preventive intervention to lower blood pressure has documented benefits. Here, the decision of develop a tool that can be used on a wearable system to monitor blood pressure values. Nowadays, blood pressure is monitored with the certificate wearable devices like Pressure Holter. There are in the market also other wearable and portable systems as the Omron Heart Guide. Both of them are with cuff, so they are not really comfortable to be used. With portable and not cuff-based devices like Shimmer but also SINTEC devices, we can evaluate blood pressure non-invasively. Moreover, with the SINTEC devices, the sensors are also forgettable and can be used without interfering in daily activities. Now, for our algorithm, we use photoplethysmogram and electrocardiogram continuous signals, respectively PPG and ECG. From them, we extract the heart rate as a time distance between two air peaks and the pulse transit time that represent the time needed to the blood to move from the heart to the distal point, for example, the hand, finger, or wrist. Then, thanks to the Bromley-Hills and Moitz-Cohen equation for blood pressure estimation, we extract some customized constants that depends on the subjects. This happens in the calibration phase, where we use labels as labels the Omron blood pressure values. After that calibration phase, we are able to estimate blood pressure non-invasively. Here, how we define the protocol in clinical environment for SINTEC sensors test and validation with respect to our reference devices, the Shimmers. We choose different clinical possible conditions. In particular, we tested this sensor for during rest activities for 20 minutes. Now I leave the floor to Francesca that will present our interface.
Hi. In order to increase the usability of the algorithm, we decided to develop a graphical user interface for both physicians but also engineers that want to use this algorithm. And this also this interface increase the usability in terms of signal visualization, signal processing, but also increase the transferability from the Shimmer devices that are the state of art in research for ECG and PPG monitoring to the SINTEC one. Now, demonstration of the use of the interface. With a simple button, we can upload ECG, PPG, and in this case also accelerometer signals, and the file containing the Omron measurements. After the uploading phase, is it possible to see the signals visualized in their full length and to select also a specific time interval in order to better investigate the signals. Then, through some radio buttons, it's possible to select the best signal processing technique between the baseline removal or the adaptive filtering. And once that the best signal processing procedure is set, there is the critical part of selecting the threshold for ECG and PPG peaks detection. This part is really crucial for the quality of the estimation. Once that the threshold is selected, it's possible to predict the result of the blood pressure. In this case, in the panels, we can see that the statistical errors are not compliant with the guidelines. So we create a technique that is based on the thresholding on a signal reference made from the accelerometer signal in order to discard the peaks that can be highly affected by motion artifact. Then it's possible to visualize in the same panels also the blood pressure estimated with the Omron device and the heart rate that is derived from the signals. It's possible to visualize the accelerometer thresholds that are used in the procedure, and it's possible to save all the results in a CSV file. And then once everything is saved, start a new session if needed. Why we decided to add the accelerometer in our procedure, it's because even if the patient is supposed to sit still during the acquisition, small gestures or small movement can introduce motion artifact and have an effect on the signal quality and in the peaks detection. As we can see, peaks are really low in the blue signals, but after a filter with LMS adaptive filter, signals have increased their quality. The other technique is to exclude peaks that can be highly corrupted by motion artifact, like in this case, where are simply noise, but if without this technique, they will be concealed in the algorithm. What we foresee as a future development in the clinical part is further investigate the quality of SINTEC signals for blood pressure estimation algorithm, especially with identifying good signal quality for cutting-edge sensors like SINTEC and compare them with the state-of-art research that are Schirmer devices. Furthermore, we would like to test the calibration that we obtain with the algorithm for recordings that last more than 20 minutes. So in order to monitor blood pressure during daily life, that is a really important aspect. And then last but not least, we would like to further investigate technique that can be used to reduce motion artifact during longer recording, so during daily activities. Thank you for your attention.
Many thanks, Valeria and Francesca. We are looking forward to knowing more about this future work. So keep us updated. And now it's the turn of the application in sports. So for this presentation, the presentation of these results, I would like to welcome Professor Matej Supej from the University of Ljubljana. Many thanks for being here, Matej.
Thank you, Sarah. Can you hear me?
I can hear you, and we can see also your presentation, so it's perfect. I think that the floor is yours, so you can start when you want.
Thank you, Sarah, for the introductory words. So I'm actually coming from two universities for this project, from Mid Sweden University, but originally as a main employer from University of Ljubljana. And our task here was to look at the application in sports, since I come from sports department and I'm head of the laboratory of biomechanics and dealing also with one foot with physiology together with the friends in the team. So if we look at the sport today or in the last decades, it's all about being faster, higher, stronger, and lately it's said together. So as we can see, sports are demanding, they are performing in very different environments, and there is no wonder why wearable technologies for such applications seems to be the way to go. And as we can see on the market, we see a large amount of different devices providing different parameters. And also what we observe is a huge increase on the market of wearable technologies. And this is why SINTEC for sport is very, very important. And we can start here. Why? Because sport needs something that is small, it's lightweight, it's not interrupting the athletes when doing their movements. And this is where we believe SINTEC is really good, because it's really small, it's really lightweight. For example, the sensor, the entire patch weighs about 6.5 grams, just to compare it here with the smartwatch, which is roughly 30 grams when it's very light, or a little bit larger one, it's 75 grams. So we can see in this respect that this technology is really light, and the feedback from our validation and studies was from the athletes that these sensors are practically imperceptible, so you don't feel it once they're attached and doing the movements, which is very good. The problem of the wearable technologies, however, is their validity and reliability. So there are many papers actually showing problems with validity and reliability. And during our work at the SINTEC project, we also have been tested different technologies, state-of-the-art, comparing SINTEC parameters with them. And we saw, for example, that core sensor for core temperature is not valid. We found similar things also for the Garmin running dynamics spot for running in place, which is not exactly what is meant for, but it's a lot of things that we see on the market that it's a problem. And that's why we put a lot of effort to look at different signals and different sports during these validations and demos, as you will see now. So one of the things that we were interested at the beginning was to look at the ECG, which is one of the parameters that's important. And here is an example on an incremental test on a cycling ergometer, looking at clear signal when the patch is well attached on the body, and with a simple peak detection, as Valeria was explaining before, we can extract heart rate. And we can see on the right side some peaks standing out, and this is when the patch was having a little bit of a lower contact between the skin and the electrodes. But otherwise, we see that comparing to the gold standard Schiller equipment or to the state-of-the-art, which is used like Polar Band or a Garmin Forerunner, we have obtained the same results. We have gone even further when we were looking on validity on step rates for running in place. So we wanted to look more in depth for this as well. We published a study on that, and for this we see actually that the SINTEC patch attached on the pelvis provided really valid results for step rates. And that's kind of interesting, particularly now for during, for example, COVID measures, when people were placed into their apartments doing some measurements and looking, or athletes and testing athletes and something like that. So it can have a huge impact in this area. And we were happy to see that the patches here were working very well. So not just to look at the running in place, so we wanted to look at also running on a treadmill, which is pretty much similar to the normal running, and we obtained the similar results, but in this case we were able to look at also the reliability, and in both cases the sensors developed by the SINTEC project show useful data. So on the left side, this shows basically the reliability, and on the right side we see the validity. And if we put this in a different type of diagram, we see high validity of these sensors in running in place with high correlation coefficients, and acceptable reliability, what we see on the right side. So we were very happy about that the sensors can be used here. And knowing this kind of technology, then in the next step can be used also for the clinical application, which is kind of related to sport. And here we have been looking at patients after a severe unilateral ankle sprain, walking on a treadmill indoors and walking outdoors, and looking at the symmetries, what they have after the normal rehabilitations has already been completed. So unfortunately, I cannot show you now the results because they are in process, but the data has been successfully collected. Another part from running and walking is to look at more a demonstration. And for this, we have put even larger efforts, particularly in the ski mountaineering, which is the next Olympic sports in the 2026. And the good part is that you can do it indoors and outdoors, and that's why we have chosen this one. And for this, we have equipped the athletes with a lot of different sensors. And of course, particularly what I want to present now is with the SINTEC sensors. The tests were actually multiple. So the first one was incremental test to know the levels where we want to test the different lengths of the poles in the second part. So it's actually kind of a 4 tests for each athlete in this demonstration. And from the accelerometers, we received data like that from the entire incremental test, which looks very promising from the distance. But when you enlarge these signals, we see that we have really nice results, which can have a direct peak detection from the sensors on the pelvis. And looking at the sensors that are actually attached on the skis, we can very well define what is the propulsive or contact phase during ski mountaineering and what is the recovery phase in between. And yeah, doing a little bit of the signal processing, so filtering and then subtracting the gravity and then using algorithms for abrupt changes in the signals, we have found a really good signal processing model that we can subtract this kind of contact and recovery phases in ski mountaineering walking. And knowing this, we performed the 3 tests with different lengths of the poles. And here is some of the results of one of the athletes. And looking at the graphs here on the left, for example, we can see that with different lengths, we have different contact times on one side. And on the other side, we also see that some of the pole lengths induced larger asymmetries between the left and the right side of the body, which is another interesting result. So we actually received, by using these signals, very important information for the athletes and also for the study that we are doing with different pole lengths. So another more feasibility demonstrator at the moment, because of the pretty poor conditions on the snow, is this. So we can see that by using the SINTEC developed technologies, we can either record the data on board on the sensors, which can be useful, for example, when you're outdoors and there is no connection to the phone network. That's one of the possibilities. For example, here, where we were on glacier on 3,000 meters altitude. And another option, when you have a good connection with the mobile network, is to have real-time monitoring, which is another option. And as Robin presented earlier, implementing the FED IBC communication, we can have actually wireless communication underwater in the future. So one of the maybe final slides or final words, it can be, we have also published a paper as a SWOT analysis highlighting the strengths, weaknesses, opportunities, and threats of the smart patches for sport, which is kind of a summary of what I have briefly presented during this short presentation. So thank you for your attention, and if you have some further questions, I can answer this later.
Many thanks, Matej. Very nice presentation and very interesting results. I've said before that we have already 2 questions. If someone has any other question, please, you can write in the chat. You can think about it and write in the chat, or also put your hands up. But before the time for a question, I just want to show you what we have developed for you, because during this last month, we have decided to develop a really nice video that shows all the results obtained in this project. This is the first time we share the video, so you are the first people that can see the video for the first time, and we are really proud of this work that have been developed together with all the partners, and it is the result of the collaboration of Warrentab with Uppsala University, Mycronic, MySphera, Evalan, of course, ST Microelectronics Links Foundation. So all the partners together have decided to create this sort of summary of all the things, all the results we have achieved. So the video, it's a little bit long. It's about 8 minutes. So please stay tuned, watch it all together. And after the video, we will able to answer to your question. I see that there is another one in the chat, so very well. If you don't mind, we will answer you, Christina, after our video. So I will share my screen, and I hope you can enjoy this work that has been a really tough work, but you will see that it has been really, okay, I have to include the audio, sorry. It has been a really tough work, but really worth it. So the stage is mine now, and please enjoy the video.
Smart wearables are the next step in the consumer Internet of Things, wearable and continuous remote patient monitoring evolution. This market is one of the most vigorous over the coming years. But are we sure that the existing wearable technologies are a good option? When we need to evaluate athletes' performance in extreme weather conditions, are actual technologies comfortable and precise in monitoring health parameters? For example, heart rate. The European Commission invested about €4 million in 2017, and a group of 8 partners with complementary skills started to develop a groundbreaking technology. The developing process necessary to build a wearable and stretchable smart patch started at Mycronic with the collaboration of Uppsala University.
SINTEC is an EU-financed research project with the goal of developing and manufacturing a soft, stretchable physiological monitoring patch and integrated information infrastructure, with the goal of being used by athletes, in healthcare, and actually by you and me. The patches that we're developing or have developed in the SINTEC project offer insight into how our bodies actually work. This can include optimizing training for athletes, reactive monitoring of those that are ill, and proactive monitoring of those that aren't, that are healthy and want to stay that way. The patch itself consists of both a hybrid encapsulated sensor platform that can be integrated with a soft, stretchable, conformally coated patch. Both of these have been designed and manufactured by our partners at ST Microelectronics and Uppsala University, together with ourselves and our other partners. The sensor integrates seamlessly with the patch itself through a simplified USB interface. When we came into the SINTEC project from Mycronic, I'll have to admit that we were focusing mainly on the technological aspects of assembling a novel physiological monitoring device. But during the project, I've come to realize that we're doing so much more. To begin with, we are actually both designing and manufacturing a truly novel physiological monitoring device. This is both the soft, stretchable substrate, the dedicated sensor package, but we can also use multiple devices connected through a novel infrastructure interface. And not only that, we're transferring the signal itself through the fat layer of the body. This is truly innovative. Finally, we haven't forgotten the environment. Our manufacturing and assembly design has been performed with an eye on sustainability. Our manufacturing is based on Mycronic's strategy of digital production, and this combines material deposition, placement of components, conformal coating, and inspection.
The SINTEC Smart Patch is particularly efficient in elite sports. Let's see why. Mate is a former elite alpine skier and is now a high-level recreational ski mountaineering and a professor teaching students at the Faculty of Sport. He is interested in various electrophysiological parameters, but is currently trying to improve his performance by testing different ski pole lengths for uphill skiing. The associated stride frequency and stride length could be retrieved from the smart patches and the base go, both developed by SINTEC. The SINTEC Smart Patch is more comfortable for athletes compared to existing technology, and it can be used in cold winter outdoor environments.
In the laboratory settings, we are interested in his aerobic capacity and how the use of different pole lengths affects his performance. And in this scenario, in addition to the SINTEC technology, which can provide ECG, heart rate, it can also provide skin temperature, which we are not currently very much interested in. It can also provide biomechanical parameters, such as determining the stride frequency of his movements. And with this, we can evaluate his performance. But then later on, when we are going on snow, we will use also this base go as GNSS technology, and this can provide us also the speed, because the speed on the treadmill is not necessary because we adjust it. It's the speed of the treadmill, but when we are outside, this is used to evaluate also the speed. So if a different pole length will provide a better speed of the athlete. In this kind of combination, you can see that this smart patches and base goes as a hub is a really small technology, works in a star network. So all the sensors that are deployed over the body that can detect different parts of the body movement also attached to the skis. So to see how the skis are moving, when they're stopping, when they're moving in a different part of the cycle. All this is working together, and all the data is then collected in the hub and distributed over to the dashboard in the cloud, where you can control all the data in real time. And this is one of the really cool features of these new technologies, because we all know now that today everything moves to remote monitoring of athletes. And in addition, for sports like ski mountaineering, this is of particular interest because it's in an outdoor environment, and monitoring athletes is even more demanding. So this kind of remote controlling of the athletes is another level of advantage. So since this technology is really light, it has approximately 7 grams each sensor, so it's quite light, it's very thin, very slim. We believe it's a good replacement of the existing wearable technologies, and most likely it will be a real game changer in the future for measuring sports performance.
We are satisfied with our research so far, and we hope that this new tool will help additional researchers, athletes, coaches in the future.
What about health? SINTEC Smart Patch has been tested also in clinical environment. Stefano is 48 years old with hypertension problems. The doctor suggests him to monitor his blood pressure frequently for an entire day. Traditional instruments are not always available. They do not allow the normal daily activities, and they are really uncomfortable to use it all day long, most of all while sleeping. SINTEC is more comfortable and could, in a practical and user-friendly way, determine and monitor BP and ECG in a continuous way. In an innovative management of hypertension, researchers are working to make it able to give us many benefits that today's technology can't reach, like diagnose any masked hypertension, highlighting variability in blood pressure values, and nocturnal hypertension that can have an impact on the development of cardiovascular events.
The ECG, electrocardiogram, and PPG, photoplethysmogram signals are recorded with the SINTEC devices. After a quick period of calibration with a cuff-based device, smartwatch with the cuff, we can evaluate the blood pressure, the systolic and diastolic pressure, non-invasively. The new interface allows us to visualize the raw signal, the filtered signal, heart rate, the accelerometer value, and to elaborate the ECG and PPG signals to visualize and calculate the blood pressure values. The innovation given by the new interface is the ease of use for technician, physician, researcher who has access to a easy-friendly tool that they can use to evaluate and visualize SINTEC signals, but also to elaborate and extract the blood pressure values with no programmer skills.
With SINTEC, Stefano's blood pressure is registered constantly and he can continue living his normal life. SINTEC, a soft, sticky and stretchable smart patch for multiple usage and long lifetime. For anyone, anywhere, anytime.
I hope you have enjoyed our project video. We are really proud of it, so we will share it for sure during the next days on our social media and on our website. So I interrupt the presentation of many thanks. I see some hands, and we will go to the questions. Okay, so I kindly ask to the the speakers to switch on the camera, because I'm going to read some of the questions that some people have written in the chat. If you have any other question, you can read them in the chat or put your hand up. The first question is from Christina. She asked, are these patches placed inside the shoe for the running measurement? No, sorry. Sorry. The first question was, how exactly have you made stretchable connections? Class, do you want to answer?
I can do that, although I think Jan and Gustav is the experts, but then since I'm not an expert, maybe I do it better. No, not really. So the principle is that we are printing on a soft and stretchable substrate, either by capillary printing or by jet dispensing. And then we are protecting the systems. It's very much like what Gustav showed during his presentation and also in the video. So it's a digital process, so it can be very easily changed and personalized when it comes to sports or personalized medicine. I hope that is the answer you were looking for, Christina, or you can come and be more detailed.
Yes, I will contact you. Hi, class.
Hi, Christina. You're most welcome to do.
Yes,
really
I will contact you and Gustav after that.
Cool.
To know what will be the stretchability of electronic contacts, because there is where the cracks are coming. But this is detailed. We can take it later.
I can take that directly, because this was a serendipity when we started this a decade ago, that in normal systems where you work with highly conductive thin films or that are stretched but that have meandering structure, you create a very large strain, or also if it is flexible meandering composites, you create very large strains where you have the rigid component. Now, this is true also for our components, but not between the contact and the interconnects. It's only for the elastomer that is surrounding the liquid metal and the rigid component. So as long as you don't break the bonding between the elastomer and rigid component, actually the rigid component glides on top of the liquid metal. So there is absolutely no problem with fatigue between the liquid metal interconnects and the rigid contact.
That's
However,
good. That's great.
yes,
I
it's
will
great.
for sure contact you both
The
because
problem is if you stretch too much, you will have a crack between the component and the elastomer, and then you will have a leakage. So there is still you can't stretch too much.
yes, I will contact you because we have an application when I need to stretch a little bit. So then I needed your solution. Good. Thank you very much.
I think we have very good solutions here, and
Good.
looking forward to that, Christina.
Many thanks for your answer. And Christina also asked if the patches are placed inside the shoe for the running measurement.
Probably it's me to answer this question. No, we did not put it inside. We could have, but we didn't because it was easier to change quickly from one to another. But it was placed on the top of the shoe. In principle, this is when we wanted to look at the ground contact times in running. But for the step frequency, actually, we used the sensor that was attached on the pelvis. It's similar like the Garmin running pod or such sensor. So for the step frequency, that was the sensor that was used.
Okay, thank you.
Thank you very much, Matej. Another question is about skin types. So how does the patch work on different skin types, bodily sweat and hair follicles? Mauricio, do you want to answer? I think that maybe can be related to the presentation of communication.
The question, can you hear me?
Yes,
Yeah.
we can hear you a little bit far. The question is, how does the patch work on different skin types? For example, hair follicles, bodily sweat.
I mean, maybe you, Matej, I think, how we say, I have not worked on the, how we say, or the material that was composing the patches.
Okay, sorry, Matej.
Yeah, so we have done a lot of different tests through different stages of the first, second, third, and fourth generations on that. Starting with some of the patches that were irritating the skin at the beginning, and then some of the patches that were not adhesed enough. So it was a lot of work on that. And finally, we came to the solution which we believe is quite good. And this one, in our experience, and we placed on a lot of different athletes, males and females, didn't have any effect and on that. The sweating part can be a problem, but the main advice on that is that you need to attach the sensor or the patch before you start sweating. So that's one of the main things, and this helps staying the patch much longer if you put it, because if you put the patch adhesion on the skin that it's already wet, then it's typically quickly game over. So what we do in our experiments is, before they do the warm up, so at the very beginning we put all the sensors on, and then they're on. And even when we had a lot of sweating, yeah, sometimes we had problems, and then we put some additional tapes on, which is quite standard in sport because they can sweat really a lot in our tests.
So may I also add to this? So there are two things here. The stretchable printed wire board where we have our sensors are laminated with a tape. And we have chosen to use highly adhesive sports tapes because when you have large movements, but depending on what tape you use, you allow more or less sweating. And we have not studied that in details, but for sure, there are tapes that are, for example, perforated and that allows displacement of sweat much more. However, secondary, in most of our applications, we are using standard ECG electrodes, so silver chloride electrodes with hydrogel pads on top, and they do not work well with heavily sweated structures or in water. You do not get the right handling there. The solution could be that what we did in a very recent publication in Advanced Functional Materials, where we used our system but changed it to an array of microelectrodes where we had the liquid metal directly in contact with the skin. And then we could even do ECG when swimming in water. So this is novel. It's not that we have gone further on that in demos, but it really could be a game changer when it comes to sports for remote monitoring of athletes when it comes to swimming sports, because previously electrophysiological measurements in water have not been considered suitable.
Okay, perfect. Many thanks both to Klas and Matej. We have another question related to sport application. So Michael asks, how long do you think these patches will be regularly used by professional sports? And how much later will leisure time sportists be able to use this technology?
The first part, I think it depends on a little bit on how user-friendly the entire system will be. We are in the development stage, and at the moment there are good advantages, but with some tweaks, final tweaks to lift it up, I think this can be used a lot, because it's really small. It doesn't interact with the movement. I mean, it's really imperceptible, and I don't know many other technologies that are so imperceptible. Even if you use a smartwatch, I mean, it makes problems, you know, around your wrists. It's either you fix it too much and it can be a problem, or if it's not fixed too much, then it moves around. So I think in this respect, it has a good potential, and particularly it is a good part because you actually adhere it to the skin. And when you are looking for information such as acceleration, then it's very important that this is well adhered to the skin. And I think this is another advantage for this technology for the future for professional sports. So this is for sure something that can prolong the usage of this kind of technology. And we know today that athletes are using a lot of technologies regularly. So I mean, until they found a better solution, I think there is a good potential for this technology. And for the second part of this answer, maybe I can say that this is more depending on the manufacturing capabilities. So as soon as the manufacturing capabilities will be such that this will be possible to buy a lot, and when elite athletes will use that, then I'm sure that recreational athletes will start using that as well, because we know now from practice that whatever elite athletes are using, all the good recreational athletes want to have it as well. And so I see here more a problem how to distribute this in a good quantities.
And if I may jump in once again here, sorry for that. But one thing that Matti had brought up that I'm very enthusiastic about is that usually it's very difficult to handle anything but strap devices if you want to put patches under racing suit. It's very difficult to take the racing suit onto you or off you without taking away the recording module on top of the patch. Now this recording module is less than 5 millimeters high, and it's protected below the sports tape, not sitting on top of the patch, which is normal. So I think there are also strong advantages mechanically for those that want to measure to the body, but under a tracksuit or a racing suit.
Thank you, Klaas. I totally agree.
Okay, so staying in sport appliances, do you see potential in this technology for reducing injuries in sports or also to detect the signs of injury?
Yes, so there are many advances in these respects in sports where this kind of technology can be used in different applications. So one of them is to monitor the activity for our training. Another is, for example, in some sort of signals, for example, in safety for ski bindings. So it's a lot of different potentials in the technology that is small. It just depends then on how to trigger and how to find the right trigger values for the signals that you can use for this kind of applications. So I think yes, this kind of technology is a possibility to be used in this respect as well.
Perfect. Many thanks. I hope that we have answered to Michael and Tasnim, questions. Then we have a question from Elena Kukarenko, that is our project officer from the European Commission. Elena, many thanks for being here today.
Many thanks for this very good presentations.
We are very
happy. Very interesting.
Many thanks. We are very happy about it. So Elena is asking, apart from the reliability issues, what were the main technology challenges for the patches?
So I can at least bring up a few things. Very much was actually about understanding the failure mechanisms. So when you have failure mechanisms in laboratory, that is totally different from when you bring it up into the real life and demonstrations. So all of a sudden, we learned about things that broke without firstly understand why. That people are pressing it in a different way than we had anticipated. A very simplistic way, and it has nothing to do with a stretchable patch, but with our module. We choose to make the module in the most simple way, we believe, in a very mature way, using flexible printed circuit boards. Now, these are very well evaluated, and we did the normal evaluation test in bending structures to see that it survives thousands and thousands of bendings with very narrow movement. That didn't help, because what happened was that since it was embedded in a soft material and with rigid components, when the rigid component was pressed into the soft module, it went like a knife through the thin metal connectors. This is never used in this way for flexible materials before, and we just couldn't imagine this would be a problem. So then it was just to think again and start building things. So failure mechanisms in the real world makes it difficult for a scientist that are more material scientists than really working with medicine.
Thank you very much.
Another question from Elena.
Yeah.
How, yeah, I read it, or if you want to ask.
I can ask myself, so thank you very much, Sarah. So it's very curious. What did you reach in terms of reproducibility of the results? Because obviously you had different groups of people to test on, ranging from, say, active people to sportsmen to patients. So for these different groups of people, how reproducible results were for patches? did you make any conclusions?
So I can answer from the sports application. So we have been testing reliability, which is the parameter that shows these kind of things with in running on a treadmill, and we have found quite good reliability. So I could look exactly the numbers, but the reliability was quite good. So that means that the reproducibility of the parameters is quite high. Also, the algorithms for detecting the parameters that we have seen were actually quite valid. So which means that once we attach the sensor provides good, accurate signals, which can be then used in further processing. So, which was quite good to see. Also, the sampling frequencies that we have in this kind of measurements were high enough. Actually, we were quite surprised in the validation study for running in place that our validity was higher, but just a bit than the gold standard equipment, which was recorded on a higher sampling frequency, actually.
Okay, thank you very much. And how about some comments about clinical work?
Hi. Unfortunately, we hadn't the opportunity to test in hospital at the moment, but we have tested algorithm with some signals and in Links Foundation. And even if we tried also a lot with Shimmer, the algorithm works really well with people with a similar BMI, even if it's not really discriminant features. So we have a high hope that we will have the same results with the SINTEC devices because we at the moment with the algorithm that we have developed, we have been compliant with national and international guidelines for blood pressure estimation.
So did I understand correctly that you didn't manage to do the trials on patients?
We have had some problems with the sensor.
Yeah, we required to the bioethical committee of the hospital the possibility to test the sensor in clinical environment, not directly on patient, on volunteers,
sure.
we can say. And we will do that very soon, honestly, because we have now the okay from all the committee, and next week we will start the clinical test, the testing clinical environment. So, and after, as Francesca said, after this very brief period of calibration, we are able to personalize in some way the algorithm to the single person, to the single volunteers, and obtain good results.
Thank you very much. And finally, what's next for SINTEC? Obviously, you have several promising results in various fields, which are very important for different areas in European strategic research agenda. So what's next for SINTEC? Do you think about any, I don't know, follow-up activities on one front or another?
Yes, if I may. So we have already passed stage 1 in a proposal that we hope will be a follow-up. The reason for that is that, I mean, already 6 years ago when the Commission initiated these things, and then we started 4.5 years ago with it, people perceived the chance. But now when we see the extreme rise with continuous remote monitoring of patients, we understand that there will be used tens of billions of smart patches yearly, and we're talking about hundreds of billions of cost reductions for only the European Union, not the patches itself, but the cost for patients monitoring. However, that will be quite a lot of waste, electronic waste, because we're talking about disposable patches, number one. Number two, all patches today are made of crude oil, plastics, and burnt or landfills. So if it's landfilled, it's a lot of microplastics systems. Hence, we will try to make these in biopolymers and biodegradable to enable legislation and a more sustainable handling of disposable electronics. And if this can be used also for patches, there are good chances that it can be used in any disposable electronics in the long run. So this is one of the things. Otherwise, Mycronic assumes, if I understand correctly, that in next year there will be possibilities for any customers that want to discuss and test the capacity for production of these systems. And Evalan believes that the base code developed here will be a product within a year. So we are talking about productization of two systems directly coupled to this system. And I'm quite sure that quite much of the work that STMicroelectronics have done and Mysphere has done is brought into their technology portfolio of productions and availability. But we have two direct productifications coming out of this project.
Thank you very much.
Many
So,
thanks, Klas.
Thank you everyone for all the good questions and answers. I'm sorry that things went way beyond the timetable. We should have brought in the Q&A into the timetable. And unfortunately, of course, a few have left, but I'm proud to see that so many of you still have remained. And if nothing else, I would just like to conclude with heartfelt thanks for you joining here, and heartfelt thanks for all the participants in the SINTEC Consortium. It's been really an honor and pleasure working with you all. Thank you.
Thank you very much. Thank you for having participated to this webinar. We will share with you a short questionnaire that I will kindly ask you to fill in. Michael is putting his hands up.
Short question. Let's go then, Michael. What was it?
Sorry, no. Thank you one more time, but I only wanted to clap, but I found the wrong button.
No problem, and thank you for that, Michael.
But yeah, so clapping like with my voice now. Thank
Good
you
to see
very
your
much.
voice. So please help us with your feedbacks in the questionnaire we will send you after this event. Many thanks. I take this opportunity also to say hi to Clara, that was one of our colleagues in the first part of the project, and she's now here. Hi, Clara. And so many thanks to all. We will share the video on our project website. And if there are any other questions, you can write us to sintecproject@gmail.com, and we will please to answer.
One more teaser before you leave us.
Okay.
Please understand, we were not able to do everything we wanted, and we are still dedicated. So we are producing more patches also after this project, I mean, the patches we have now, to continue collaborations with links and with the MIT University and the University of Ljubljana for sports performance applications. So stay tuned for seeing new publications within a year on these demonstrations. Thank you.
Sure.
And bye again.
Goodbye.
Bye.
Bye-bye.
Thank you. Bye.